Hello and welcome to InsideWi-Fi, Video 28. Receiver sensitivity, the hidden key for reliable Wi-Fi connection. If you missed my earlier videos, please check them out, they're all connected and build on each other. When most people set up Wi-Fi, they usually think about speed or signal bars, but there's another hidden factor that makes a huge difference, the receiver sensitivity. It's what decides how well your device can hear weak signals and stay connected. By paying attention to this, you can get faster speeds, wider coverage, and a much more stable connection wherever you use Wi-Fi. In a noisy environment, someone with sharp hearing can still make out faint whispers, while someone with poor hearing may struggle to catch even louder speech. Receiver sensitivity works in much the same way as devices with high sensitivity can clearly detect weak Wi-Fi signals, whereas less sensitive receivers require stronger signals to maintain reliable communication. What is receiver sensitivity? Receiver sensitivity refers to the lowest signal level at which a device can reliably decode data. If the signal drops below this threshold, communication becomes unreliable or fails altogether. Why receiver sensitivity is important in Wi-Fi? Receiver sensitivity directly affects range. A device with better receiver sensitivity can pick up signals from further away, extending the effective coverage area of your Wi-Fi network, thus improving the range. Better performance in noisy environments. In congested Wi-Fi environments like apartments where many networks overlap, a device with good sensitivity can better distinguish your Wi-Fi signal from interference, leading to more reliable performance. Throughput. Even if a device connects, better sensitivity means it can potentially decode signals at higher modulation rates even at lower signal strengths, leading to faster actual data transfer. What are the factors affecting receiver sensitivity? Factors affecting receiver sensitivity are thermal noise power (KTB), noise factor (NF) of the receiver, minimum required signal-to-noise ratio (SNR). What is thermal noise power, KTB? This is the absolute minimum, unavoidable random electrical noise present in any electronic component due to the thermal agitation of electrons. It's often referred to as white noise as it's theoretically spread evenly across all frequencies. Higher temperatures both ambient and within the device itself increase electron agitation, leading to more thermal noise and thus worsening or degrading sensitivity. A wider signal bandwidth, example, using 40 MHz or 80 MHz Wi-Fi channels instead of 20 MHz, means the receiver is listening to a broader range of frequencies, thereby collecting more thermal noise power. This effectively raises the noise floor, which degrades sensitivity for achieving a particular data rate. What is noise factor (NF)? Noise factor represents the internal noise of the receiver. A higher NF make it harder for the receiver to distinguish the actual Wi-Fi signal from its own internally generated noise, leading to lower sensitivity. What is minimum required signal-to-noise ratio (SNR)? The lowest SNR at which the receiver can reliably decode the signal depends on the modulation scheme, data rate, environmental conditions, device speed. Lower SNR requirements lead to better sensitivity. Formula for receiver sensitivity. S equals 10 log 10 of KTB plus NF plus SNR. Where S equals receiver sensitivity in dBm, lower values indicate better receiver performance. K equals Boltzmann constant. T equals absolute temperature in Kelvin, higher temperature increases thermal noise and worsens sensitivity. B equals signal bandwidth in Hz, wider bandwidth raises noise power and degrades sensitivity. KTB equals thermal noise power within the bandwidth in watts. NF equals noise factor of the receiver in decibel, SNR equals minimum signal-to-noise ratio needed to decode signals in decibel, lower SNR requirement improves sensitivity. Receiver sensitivity of products. Receiver sensitivity varies across devices. Typical 802.11g products offer around -85 dBm, commercial Wi-Fi devices may reach -105 dBm, and professional-grade receivers can achieve up to -120 dBm. Sensitivity effectively doubles with every 3 decibel increase in signal power. Values like -83 dBm often represent sensitivity measured at 11 Mbps with a burr of 10 power -5. Receiver sensitivity at stations. Since stations generally have lower receiver sensitivity than access points, coverage is often limited by the uplink, that is, the station's transmit power. If an AP transmits at full power, station may see strong signals but still suffer poor connectivity. To balance performance, reduce the AP's transmit power to just above the station's sensitivity, helping align uplink and downlink MCS levels. Receiver sensitivity based on packet error rate. Wi-Fi devices communicate by sending and receiving data in packets. A single bit error in a packet can render the entire packet unusable, forcing retransmissions at the MAC layer. Therefore, PER directly reflects the end-to-end reliability and efficiency of the wireless link. PER gives a better indication of the quality of data being passed up to higher layers of the network stack. A high PER means more retransmissions, leading to lower effective throughput and higher latency, which directly impacts user experience. Example, buffering video, lag in online games. What is packet error rate PER? PER is the ratio of the number of incorrectly received data packets to the total number of packets transmitted within a specific observation period. It's often expressed as a percentage, example, 10% or a fraction, example, 0.1. What is receiver sensitivity test? The receiver sensitivity test ensures that the device under test DUT can receive data with a maximum packet error rate of 10% at a specified minimum signal power level. During a receiver sensitivity test, the DUT is typically connected to a signal generator that transmits known Wi-Fi packets. The power level of this signal is gradually reduced until the PER consistently reaches or exceeds the 10% threshold. The signal power level at which this occurs is then recorded as the receiver sensitivity for that specific MCS. The maximum 10% PER condition. When the signal strength at the receiver's antenna drops to the specified sensitivity level, for example, -82 dBm, the device must still be able to successfully receive at least 90% of the packets transmitted to it. If the PER exceeds 10%, the signal is considered too weak for reliable communication at that data rate. Varying by data rate MCS. It's important to note that receiver sensitivity is not a single value for a device. It varies significantly depending on the modulation and coding scheme MCS being used. Higher data rates which use more complex modulation like 256 QAM require a stronger signal and thus have worse sensitivity values, while lower, more robust data rates like BPSK can be decoded at much weaker signal levels. Receiver sensitivity and real-world impact. Better sensitivity extends Wi-Fi coverage in homes, offices, and outdoor networks. High sensitivity helps in crowded environments, ensuring smoother streaming, gaming, and video calls. Low sensitivity devices may struggle even if they connect, resulting in buffering, dropped calls, or slow speeds. How to optimize receiver sensitivity? Choose devices with higher receiver sensitivity ratings. Use the 5 GHz or 6 GHz bands for better performance in high-density environments. Reduce interference by selecting the least congested Wi-Fi channel. Keep firmware updated for optimal signal handling. What will happen when the noise floor is above receiver sensitivity? When the noise floor is above the receiver sensitivity, the receiver won't be able to hear the Wi-Fi signal. In our next video, let's see unseen zone around Wi-Fi signals, the Fresnel zone. Thanks for watching. Do post your comments.